So we've been working on linear drag and other types of drag, but I want to go over all of the details you need to be able to make a graph of the velocity and position for an object moving with linear drag in horizontal motion. And then we're going to make a model of it. So we're going to actually make 4 graphs. Make a graph for velocity, position, and then I'll do another way to do the same things. Okay, so it's going to be great fun. Now, if an object is moving with linear drag, it has this drag force proportional to the velocity, where b is just some parameter, depends on the diameter of the object, and beta depends on the materials in the thing. It doesn't really matter. It's just constant. And so then you have this. The net force is mass times acceleration, dv dt, is equal to negative bv. If you solve that equation, and I did that in a previous video, my playlist is down below, you can see it there. Then we get this for the velocity as a function of time, the initial velocity v0, e to the negative b over bt over m, and then we take that equation and solve it for position. We get x as a function of time, it's x0, v0 over m, v0 m over b, 1 minus e to the negative b over bt over m. And so I want to graph these two things in Python. I'm going to use glowscript Web VPython and show you how to do it to make a nice pretty graph, and then all of the details associated with it, and then I'll come back here and do this another way. So if we want to make a graph, though, just to be clear, I need to have values for all this stuff. So let's say the initial velocity is 0.5 meters per second. The initial position is 0 meters. And then it has a diameter of 0.2 millimeters. It's water, so it has 1,000 kilograms per cubic meter. I can use that to find the volume. Since it's a sphere, I can find all this stuff. So let's just jump in there and write down these parameters, which I should have done already, but I didn't. And then we'll make a graph. Okay. And I'm going to give you the code for this, so don't worry about that. So here I am in glowscript Web VPython. I'm using trinket.io because it's just easier to share and stuff. So let's just start typing in some stuff. If you're not familiar with Python, I think that's okay. I'll just keep on going anyway, and then you can catch up with other stuff. It'll be fine. So I'm going to enter my parameters here that I have. I have m equals I have d equals 0.2. Let's say 0.2 times 10 to the negative third. E negative 3. I'm not going to put units. I'm not even going to put comments because I want to go fast. R is the radius of that drop. It's just going to be d over 2. What else do I have? Rho is 1,000. So beta is 1.6 times 10 to the negative 4. And I got that from another problem. It's just a constant. It doesn't really matter. So b is equal to beta times d. I need the mass. So the mass is going to be based on the volume. So the volume is 4/3 times pi times r cubed, and then the mass is going to be rho times v. Now I need the initial position, x0 equals 0. That's an O. Whoa, x0 equals 0. v0 equals 0.5, and that's that. Okay, and so what I'm going to do is calculate the velocity at different times, and then I'm going to move to a new time and calculate the velocity, and plot it. So I'm going to have time. I'm going to start at 0, and let's just have a time step of 0.01. Okay, so now how do we make a graph in Python? So the easiest way is just to do this. I'm going to say I'm going to call it the velocity graph. So I'm going to call it FV for a velocity function. The name doesn't matter. You can pick whatever you want. Equals G curve. Now, this will not work in Python. It has to be glowscript Web VPython. So if I go up here to let me save this. Plotting linear drag. Save. Because I'm afraid that might accidentally start a new window, and that would make me sad. Did it save? Run this. I guess it saved. I don't think it did. Because normally, there it goes. There it's saved. Okay. So if I go up here to new trinket, you can't see the whole thing. Let me move this over a little bit. You don't want to do Python. It doesn't have the graphing stuff built in. You want to do glowscript. Okay, so let's not do that. Let's just go back down here. And I've already done that. And it'll automatically put this glow script up there. And that has built-in graphing, this G-curve. So this G-curve is a line connecting any points that you plot. So I can plot, let's just plot 2 points. The way you plot a point is with fv.plot, and then you give it your horizontal value and your vertical value, and it plots it. So let's say 1, 1, fv.plot 2, 2. Boring graph, but that's fine. And then there's my graph. There's my first point down here. There's my second point down there. Okay. So let's go and make a graph because I need to calculate all this stuff. So I'm going to start off with a loop. So I'll say while t less than 0.3. In Python, loops are done with a statement like that and a colon. And then everything that's tab indented is part of that loop. So let's just say print t. And then I'm going to say t equals t plus dt. So t equals t plus dt increments the value of t. And then it goes back and does it again. So this will just print out all my values of t. I'm just doing this to show you how a loop works in Python. Oh, I clicked the wrong one. Play. So there's all my values of t. It printed out. Yay. Yippee. Awesome. Okay, but I don't want to do that. What I want to do is to instead calculate the value of the velocity and plot that. So I'm going to use this equation that I wrote down. I'm pointing to it. You can't see it. My velocity equation. So I'm just going to calculate the velocity. V equals V0 times E. E in raised to power in Python is exp. And then it's a function. I put it in there. And then it's going to be negative b times t divided by n. Make sure that you use real orders of operation or real operators. You can't put V0E. It doesn't know what that means. You have to explicitly say multiply. So that calculates the velocity. Now I'm going to plot that. fv.plot tv. And then I'm going to increment v, and then that's that. Check that out. That's what we'd expect, right? It starts at a velocity of 0.5 meters, and it decreases in speed like that. That's what we would expect. But you'll notice there's no labels on these axes, so let's fix that. So G-curve just plots that curve. If you don't say anything about the axis, it just leaves it blank. But I can make an axis with another object called a graph. And I'm going to give it a name. You don't have to, but I'm going to. G1 equals graph. Now I can give it a whole bunch of properties, like title equals linear drag. You can put whatever you want there. X title that's a reserved word. That's a reserved property of the graphed object. You can look up all these. glowscript. In glowscript, if you go to help up here, and then you go, sorry, it's to work with 3D object graphs. All these properties are there, so you can check that out. Okay, we're back here with our graph. X title equals time in seconds. Y title equals V in meters per second. The other thing I like to do, you don't have to, but I'm going to, I like to give it a width of, let's say, 400, height of 200. And that just makes the default graph's kind of big on my display because I've zoomed in order for you to see it. And that's all I have to do. Now it's going to put that graph in that, since it's only graph there, it's going to put that function in that one. And there you go. That's a pretty nice graph, you have to admit. Okay, you can change the color. I do like to change the color. So in this, I can put color equals color.blue and then run it. Very nice. Okay, now I want to make a plot of the position as a function of time also. I could just change this graph, but I actually want to make two graphs. I'm going to put another graph below it. You could just, because they're not, you can't plot them two together. They're two different things. So let's make another graph. Actually, I'm just going to copy this. Copy that and paste it and call it G2. And I'm going to get rid of the title because I don't really need a title for the bottom one. And this is going to be X title is time, Y title is X in meters. Now, if I have two graphs, I need to tell, it would figure it out, but I want to tell Python which function goes in which graph. So up here for fv, I'm going to say graph equals g1, because that's the name of the graph I want to put that in. And then down here, I'm going to make another graph called fx equals gcurve, color equals color.red, graph equals g2. So now it knows which function to go in which graph. It's the same size though. So now all I need to do is to calculate my x position. So again, I'm looking at my paper right here on the side, and I have x equals x0 plus v0 times m divided by b. I'm going to put that all in parentheses because I get paranoid about order of operations. Times 1 minus exponent negative b times t divided by m. And I'm going to plot that one too. Fx dot plot tx. Run it. Check that out. I mean, that's pretty nice. I mean, that's like professional quality graphing right there in just a few lines of code, which I'm going to give to you down below. There will be a link to that down below. You'll notice that the graphs don't completely line up because these labels here, but you can fix that. I'm not going to worry about it right now. I don't want to spend too much time on that. So those are my two graphs. You can change the initial velocity and stuff and see the new graphs. But now I want another way to calculate the motion for this, make these graphs. Okay, so let's go back over to paper, and I'm going to show you how you can do this without integrating, which is what we did before. Okay, so let's take this equation right here. I'm going to rewrite it. F, and this is in one dimension, equals m. I'm going to write this as ma equals negative bv. That's all I need. So suppose I break the problem into small time steps. Delta t equals 0.01 seconds. During that time interval, I can calculate the acceleration, a negative b over mv. Now let's assume, and of course you know when you assume what you make, that's fine. Assume a equals constant. So whatever I calculate, I'm going to assume that that's a constant acceleration. It's totally not constant, right? If there's an acceleration, the velocity is going to change. What's going to change the acceleration? That's the problem. But if my time interval is small enough, it's not a bad approximation, and I can always make that smaller. Okay. So if the acceleration is constant, then I can use the following definition. A is delta v over delta t. So at the beginning of this time interval, I have v1, and at the end of the time interval, I have v2. So I can say the change in velocity is just going to be v2 minus v1 over delta t. I can multiply both sides by delta t, and I get v2 minus v1 is a delta t. And then I can add v1 to both sides, and I get v2 equals v1 plus a delta t. So I calculate the acceleration, and then I use that to find the velocity at the end of the time interval. Okay, which is wrong, but just kind of wrong is kind of right. Okay, now let's do the same thing. Let's assume v equals constant, and you may be thinking, and you should be thinking, but wait, we just showed that v changes. I know. Okay. So if v is constant, I'm going to use this as my value for v that is calculated. I can say v equals delta x over delta t. That's the definition. And if I have x1 at the beginning going to x2 at the end, then I can say this is x2 minus x1 over delta t. Now if I multiply both sides by delta t, I get x2 minus x1 equals v2 delta t. I'm going to call it v2 because I just calculated that velocity. Now I can add x1 to both sides. I get x2 equals x1 plus v2 delta t. And that I've done it, right? I started at the beginning of the time interval. I calculated the acceleration. I found the velocity at the end of the time interval. I found the position at the end of the time interval. And then I'm going to do it again. I'm going to go from x, I'm going to go another delta t. I'm going to go from x2 to x3, v2 to v3. And then I'm going to do another time interval, x3 to x4, v3 to v4. And so if I did those calculations, that's not too hard, but it'd be 1, 2, 3 sets of calculations. I have to do all these things. Every time I get to the new interval, I need to recalculate the acceleration because the velocity changed, and then use that to update the velocity, use that to update the position. But you'll see here, I only have 0.01 at the end of this time interval, 0.02, 0.03. It only did 0.03 seconds worth of stuff. If I want to get to 0.3 seconds, I'd have to do this, what? 30 times. Okay, which isn't too bad. But it's too bad that I don't want to do that because I am a lazy person. And so instead, I'm going to get the computer to do it. So let's get the computer to do these calculations. This is called a numerical calculation. Numerical calculation. I'm always afraid I'm going to misspell stuff. And this is the Euler method. And there are different Euler methods. Some people would call this a different method too, but there are more sophisticated methods to solve this. This is a very unsophisticated method, but it works very well and it's easy to understand, so that's why I'm going to do that. Okay, so let's jump over to the computer, use the same code, and plot this in that code. And I'm going to show you how to do it. It's going to be great. Okay, switching back to computer, here we are. Okay, so I already have everything that I need. I'm going to need to add 2 new graphs, right? I need a new velocity graph, a new position graph for my numerical calculations. And I need a new position variable and a new velocity variable. So let's do those first. I'm going to call this xn equals x0. xn is my numerical value of x, because I calculate x the other way too. I want to have those two separately. I need to have an initial value to start with. I need to know what value I'm starting with for x. So I need to give it that. I need initial conditions. I also need initial velocity. Vn equals v0. So they have numbers. It is possible to solve these kind of equations with where I know the boundary conditions, but it's a different solution. Okay. Now I need down here, I'm going to make a new graph. So let's call this fvn equals g curve. I'm just going to leave it as, let's make it green. Color equals color.green. And then graph equals g1. And then down here, xfxn equals g curve. Color equals color.green. It's also green. Graph equals g2. Okay, so down in my loop, I've already calculated the analytical velocity and position. So what I need to do now is to calculate the acceleration. So a equals negative b times v n over m. So you'll notice that I'm using the numerical velocity. I'm using the numerical value for the velocity. Okay. And whatever that is, when it starts off with the initial velocity. But I calculate the acceleration. Now I need to update the velocity. Vn equals Vn plus a times dt. So that dt, that's my time interval of 0.01 seconds. Multiply it by that acceleration, add it to my velocity. And this is, just like down here, this is an update equation. Take whatever value this Vn is, add a times delta t, and set that equal to the new velocity. So it's not an algebraic sign. The Vn's don't cancel. Now I can write down the position update equation. Xn equals xn plus Vn times dt. And that's it. I already update time down later. So I just want to plot those two things. So fvn.plot tvn, fvxn.plot txn. That's it. Let's run this thing and see. I didn't get any errors so far, so okay. Wow. I'm on a roll today. That's a roll right there. You'll notice that these two curves are not exactly the same. Because remember what's happening. I am calculating using a time interval of 0.01 seconds. And so that's actually kind of a long time interval in this situation. I can make it smaller and I should get a better estimate. But there's my velocity. It fairly matches fairly well. Position's a little bit different too. Matches fairly well though. So let's go up here and make a smaller time interval. 0. And there you go. Okay, they're right on top of each other. Right on top of each other. I want to do one more problem just for fun. Let's change this to the y direction. So everything's in the y direction. So the first thing I'm going to do is let's just change all these x's to y's. And you don't actually have to do that, but I think everyone will be happier. X, y, that's going to be y. That's going to be y. I want to do it in the vertical case. I should change this to y. I'm going to keep the name of the graph as the x just to spice things up. Oh, did that change? Oh, it did change that. So it's going to be y. Y. V is in the y direction. And then, this is y. It should, and if I just change the name, it should still work the same way. And then just change this to y. I shouldn't have done this, but okay. Now I'm going to get an error. Watch this. I'm probably going to get an error. Oh, it worked. Okay. So it's in the y direction. But now I want to add the gravitational force. We can get an analytical solution for this, and I did this in my playlist that I have linked down below. But I want to change the numerical model. I want to show you how easy it is to do that. Let's go back over here to the paper. So suppose that I have my object falling down like this. In this case, so it's moving this way. That's v, which could be negative. So then I have a downward gravitational force, mg, and this F drag up, pushing up. So if I write F net, it would be equal to negative mg minus bv. So it's still minus because in the y direction, if the velocity is negative, then this would be an upwards pushing drag force. So that works, right? And this actually works even if it's moving up. If it's moving up, then the drag force is down. So this works either way, which is really kind of cool. Okay. So if I change this to my net force, this is actually in the y direction. This is going to be ma. So if I solve for a, I get a equals negative g minus bv over m. So instead of this is my acceleration, this is my acceleration. But if I assume that's constant, this equation stays the same, this equation stays the same. So it's pretty easy to change the motion. So what I'm going to do is take a ball, drop it from rest, so v is equal to 0, and I'm going to change my acceleration to this, and it should work. Okay, so let's do that. Now, my analytical solutions, I'm going to just turn that off because that's going to be plotting something that's completely different, and I'm not going to calculate that. So let's just do a numerical calculation for a falling ball. Okay. So over here, the first thing I'm going to do is I'm not going to plot FV and FX. Let's just run that to make sure this is turned off. Okay, that's fine. And then over here, I'm going to say I need another constant, g equals 9.8. And then I'm going to put v0 is 0. y0 is 0, v0 is 0. That's fine in a falling case because it'll fall and reach terminal velocity. So down here, the only thing I need to do is change this as negative g. That's all. That's it. I just have to add that negative g term in there. That's it. Okay. And everything else should work fine. It's calculating x and y. I don't think it really matters. Let's just leave those there. Let's see what happens and see if the graph makes sense. Okay, so in terms of the velocity, it starts off from rest. And it has an acceleration. It's accelerating at, I don't like those green. It's funny when you get a little picky about stupid stuff, but let's change that to blue. and that one to red. But, you know, everyone's got to have their own little thing, right? That's so much better. So it starts off at a velocity of 0 and starts speeding up going down because there's very little air resistance. I dropped it from rest. But eventually it's going to reach some terminal velocity over here, right? Because at some point the air resistance is going to be equal to the weight and it'll move at a constant speed. And I'll show you that in just a second. As far as the trajectory, this first part up here, it looks like a parabola because the drag resistance is very small. And then it reaches some constant velocity down here. So let's just fix this. Run it for a longer time. Let's say 0.8 seconds. I don't even know where I got 0.8 from, but I just did. And there you can see it almost reaches a terminal velocity, and that's a fairly straight line. But wait, what if I throw the ball up? This works if I throw the ball up, okay? So all I need to do is give it an initial velocity that's not 0. Let's say 0.5. And you'll notice, oh, it didn't go. Let's throw it a little bit faster because it didn't go very high. Let's give it 2.5. Let's just see. So there it's going to go up and then fall down. And the velocity starts out with some positive value. And then here's the highest point right there. It reaches 0. You'll notice down that corresponds to this time right here. The graphs are shifted a little bit, remember? But that would correspond. And then it has a negative velocity. It's falling back down. So, but the point is that I only made one tiny change to my numerical calculation, and I can represent a much more complicated situation. This you can solve analytically, but there are some other cases in quadratic drag where it's like pretty much impossible to solve analytically. Not exactly, but pretty much. So, what did I want to show you? I want to show you graphing, check. I want to show you a numerical calculation, check. Code down below, links to the playlist down below, and that's that.